So here we have a linear equation, but it just doesn't satisfy or doesn't look like our derivation or the equation that we used to derive the solution. So we want the equation to resemble that. So I'm going to divide by x squared on both sides. So y prime minus x over x squared times y equals 1 over x squared, which would be y prime minus 1 over x y equals 1 over x squared. That would mean p is negative 1 over x and g of x is 1 over x squared. The first step now is to find the integrating factor, which is mu e raised integral p times dx. So we have e raised integral minus 1 over x dx. Bring the negative out, e raised integral dx divided by x. And the integral of dx over x is ln of x. From algebra, we know that if there is a negative number, a number between e and ln, we can't directly cancel them out. So we're going to use the power rule of logarithms to move the negative one inside. Now the e and the ln would get cancelled. So we have mu to be x raised negative 1, so the integrating factor is simply 1 over x. The solution now is y equals 1 over mu integral mu times g of x dx plus c. So y would equal to 1 over x integral 1 over x g of x, and g of x we found that to be 1 over x squared dx plus c. 1 over x is x integral dx over x cubed plus c. Move the x cubed to the numerator, we'd have x raised negative 3 dx plus c. The integral of x raised negative 3 is x raised negative 2 over negative 2. And now we can distribute the x inside. So we will have x to be equal to x times x raised negative 2 over negative 2 plus c times x, which would give us x raised negative 1 over negative 2 plus c times x. And I could write that as minus 1 over 2x plus cx. Now, what is the existence interval? The largest existence interval for the solution. I can put in any value I want in this equation, but I've got to be careful in plugging in the value 0. If I plug in 0, the x value would go in the denominator in 1 divided by 2x, which would make the solution undefined. So the existence interval is negative infinity to 0, union 0 to infinity. We're going to exclude 0 from the solution. The next problem is very similar to the previous problem in the sense that it doesn't look look similar to the form that we had, which is y prime in our derivation, y prime p times y equals g of x. So what I'm going to do is I'm going to divide by x on both sides. So dy over dx minus 1 over x y equals x squared times sine x over x. The x and the x squared will get cancelled. So we have dy over dx minus 1 over x y equals x times sine x. This would mean that p is negative 1 over x and g of x is simply x times sine x. Now, in the previous problem, we had p to be negative 1 over x, so the integration factor here would be the same. Integration factor, doesn't matter. You can call it whichever way you want. So the solution now one over mu times integral mu times g of x dx plus c. So y would be 1 over x times integral 1 over x. G of x is x times sine x dx plus c. 1 over x is simply x. These x's would get cancelled, so we have integral of sine x plus c. And integral of sine x is negative cosine x. So we have x times negative cosine x plus c. Distribute the x in, so y would be equal to negative x cosine x plus c, or c times x. So the solution would be cx minus x cosine x. Here is another problem which is a bit more involved. So the first step is to rewrite it in the form that we want. So I'm going to divide it by x plus 1 on both sides. And now we can make a direct comparison to the first order linear equation that we had, which will give us p to be equal to x plus 2 over x plus 1 and g of x to be equal to 2x over x plus 1 times e raised negative x. So the next step would be to find the integrating factor. It's mu, which is equal to e raised integral p times dx. So that would be equal to integral e raised x plus 2 over x plus 1 times dx. Now, you must know integral calculus pretty well because this requires a trick. So I'm going to take the integral that we see up here, going to do it separately, and then plug it back in. How do we integrate this? Well, the trick here is to write that 2 as 1 plus 1. And the first two terms, if I combine it, it becomes x plus 1. Since we have a common denominator, I'm going to write it as x plus 1 over x plus 1 plus 1 over x plus 1 dx. Split the integrals. X plus 1 over x plus 1 is simply 1 plus 1 over x plus 1 dx. Distribute, we'd have dx plus integral dx divided by x plus 1. Integral of dx is simply x. And integral of dx over x plus 1 is ln of x plus 1. Now we can take this value and put it back in the integrating factor. So mu would equal to e raised x plus ln of x plus 1 using the properties of exponents. I'm going to split it up and write it that way. So the e and the ln would go away. I'd have x plus 1 times e raised x as the integrating factor. So the solution now y equals 1 over mu integral mu times g of x dx plus c. Y equals 1 over, we have mu as x plus 1 times e raised x integral x plus 1 times e raised x. G of x in our case is 2x over x plus 1 times e raised negative x dx plus c. Things are falling in place, so x plus 1 would go away, the e raised x and e raised negative x would go away, so we would simply have y is equal to 1 over x plus 1 e raised x integral 2 x dx plus c. And we all know the integral of x is simply x squared over 2. The 2's would get cancelled and we would simply have the solution to be y equals 1 over x plus 1 times e raised x multiplied by x squared plus c. Now, if we simply we don't want to look at or look on the negative side here, because e raised negative infinity is 0, which would make the denominator 0, and since we have x plus 1 in the denominator, if we plug in negative 1, the denominator would become 0. So in this problem, the existence interval is from negative 1 all the way up to infinity. So here we have an initial value problem, and this is a linear equation which is given right over here, and that is our initial condition. So we have xy prime plus y equals 4x plus 1. We want to bring it to our standard form, so we're going to divide by x. Perhaps I'll rewrite this, even though it is not necessary. I'm splitting up because I have a common denominator, and that would reduce to 4 plus 1 over x. Now that fits right into the form that we had in our derivation. Y prime, p, and g of x. So p is 1 over x, and g of x is equal to 4 plus 1 over x. The integrating factor is mu equals e raised integral p times dx, which is e integral 1 over x dx, e raised integral dx over x. Integral dx over x is simply ln x, so we have e raised ln of x. E and ln would go away, we simply have x. So we found the integrating factor, which is x, so the solution is y equal to 1 over mu integral mu times g of x dx plus c. Mu is x. X times 4 plus 1 over x dx, which is g of x. Let us distribute the x inside 4 plus 1 over x dx. So we will get y equals 1 over x, 4x plus x over x times dx plus c. Which would reduce to integral 4x dx plus integral dx plus c. Integral 4x is simply 4x squared over 2. Excuse me. Integral of dx is x. So y would equal 1 over x, 2x squared plus x plus c. Distribute the x inside, we will have y to be equal to 2x plus 1 plus c over x. Since we have an initial condition that y over 1 is 8, y of 1 equals 8. Which would mean when x is 1, y is 8. So we're going to plug that in and solve for the constant. That is the purpose of having an initial condition, which would give us a particular solution that would satisfy the initial condition. So 8 would equal to 2 times 1 plus 1 plus c over x, which is 1. So 8 equals 3 plus c, and c would equal to 5. So the solution, or the particular solution, is y equals 2x plus 1 plus 5 over x. And you can see that that solution is free of arbitrary parameters. So the c over here is an arbitrary parameter, and it would form a one parameter family of solutions. But because of the initial condition, we end up getting a single solution, which is y equals 2x plus 1 plus 5 over x. Here is another initial value problem, where we have things in the very standard form: y prime plus p times y equals g of x, which would imply p is negative sine x, g of x is 2 times sine x. The first step is to find the integrating factor. Which is mu, which equals e raised integral p times dx. So we have e raised integral negative sine x dx. And we know that the integral of sine x is negative cosine x. So we have mu to be equal to e raised negative of negative cosine x. So we end up getting e raised cosine x. So we have the integrating factor, which is e raised cosine x. Now we move on to the solution. One over mu integral mu times g of x dx plus c. 1 over e raised cosine x integral e raised cosine x times 2 times sine x dx plus c. We can bring the 2 out, so we have 1 over e raised cosine x 2 e raised cosine x sine x dx plus c. You may look at that integral and say, oh, let me do it with integration by parts. Don't. This particular integral can be solved with substitution. So if I let u equal cosine x, du would be negative sine x dx. So I am going to replace cosine x in the integral by u, and if du is negative sine x dx, sine x dx would equal negative du, so negative du plus c. So y equals e raised negative cosine x negative 2 integral of e raised u du plus c which is simply e raised u. Replace the u by our substitution, which is cosine x. So our solution is simply y equals e raised negative cosine x times negative 2 e raised positive cosine x plus c times e raised negative cosine x. So these two terms would cancel out because the bases are identical. You add the powers, cosine x minus cosine x is 0, and e raised 0 is 1. So we will have the solution as y equals negative 2 plus c e raised negative cosine x. We do have an initial condition, which is when x is pi over 2, y is 1. So plug in pi over 2 for x. So 1 would equal to negative 2 plus c times e raised negative cosine pi over 2. And negative cosine pi over 2 is 0, so negative 2 plus c e raised 0. E raised 0 is 1, so 1 would equal negative 2 plus c, which would imply c is 3. Therefore, the solution here is y equals negative 2 plus 3 e raised negative cosine x. And the existence interval here, you can plug in any value for x, so negative infinity all the way up to positive infinity.